satisfiability. That's the first very basic reasoning task we need. Next one, subsumption. So here we want to check whether in every model some concept is a subset of another concept. Okay? And why do we want to do this? Well, first of all, we really want to understand the relationships between the different concepts that we've expressed. So some things might not be put there explicitly in the ontology, but in fact by chaining together, doing some reasoning, we're actually able to infer new relationships. Okay? In fact, one particular, a more specific task than subsumption is something called classification. So here what we do is we take all of the atomic concepts that appear in our ontology, and we do all the subsumption checks to see which ones are more general or more specific than each other. And so we can organize our ontology, our atomic concepts, into basically a hierarchy. Okay? And this is very useful for navigating the ontology, for seeing what's in it, and also, so both for understanding it and also for debugging it, because satisfiability, okay, we definitely want our knowledge base to be satisfiable, but that's a pretty minimal guarantee on the quality, right? The fact that there's no contradictions doesn't mean that it gives us the information we want. And so if we, for instance, compute all the inclusions between the atomic concepts, and then we see that there's either an atomic subsumption, like there's an inclusion that is missing, or there's an inclusion that is there that we don't think should be there, this gives us some other additional information about what might be wrong with our ontology. Okay? So this is another useful tool for checking for errors and just checking that the modeling that we've done is correct, or as far as we can tell. So let's take another example here. So here I have something a little bit more complicated. Okay, so this is a bit as before. Giraffes are animals that only eat leaves. Trees are plants, okay? Leaves are parts of trees. And now I have a bit more complex definition. I decided to write it in another way. So now I say that herbivores are animals that only eat things that are not animals. Okay, maybe this is not the right way to do it, but someone might think to write it in this way. And they only eat things that are not parts of animals. Okay? Okay, so this is one way you might think of writing it. And then we have this last statement here, which maybe looks a bit complicated, but it's really not very hard. It just says that if I'm an animal, or if I'm a part of an animal, then I can't be a plant, and I can't be a part of a plant. Okay, so it just states that this is disjoint with that, this is disjoint with that, and it's just so I don't run off the slide, I put them all together in one. But that's all that it says. Okay, and so my question is it the case that my knowledge base implies this subsumption? Do I have that this axiom is entailed?
No, because giraffe is an animal, and then the animal who eats leaf, it is the animal who eats not animal, and who eats not plant animal.
Okay, so you think it's good?
Classes.
Well, no, I mean giraffe is not equivalent to herbivore, but...
No, I mean the class is something who eats leaf, and something who eats not animal and not a part of animal.
Okay, so they're not equivalent, but there is a subsumption. So indeed, if I only eat leaves, it means that I only eat things that are not animal, and I only eat things that are not parts of animals. So they're not equivalent. These expressions don't mean the same thing, but indeed this is stronger. This implies this, and this implies this. When you put it together with these, you need these three other axioms. You have to chain the reasoning together, and then you're able to infer indeed that that we satisfy these conditions, and so giraffes are herbivores. Okay, good. Okay, so another important thing is that we'd also like to do some reasoning with our A-box, right? So we have some data, we want to be able to do some reasoning on it as well. So for instance, a very simple task is to find all those individuals that belong to a given concept C. So I have some class description, I want to identify those individuals that satisfy this class, or that belong to this class, okay? Or you could do it vice versa, you could pick an individual and you want to find out which classes it belongs to, okay? And this is a very simple way of querying our A-box, okay, our set of facts. And then another way of doing some querying which is a lot more complex, and it's become popular in recent years, is conjunctive query answering. So I won't go through all the definitions because it would be long and it's really not necessary. But the idea is that we're going to have some sort of, we're going to have a conjunctive query, and I'll give an example on the next slide. And we want to find those tuples of individuals that always satisfy this query. They're basically answers to it. And the idea is that these conjunctive queries correspond to a very standard class of queries in databases. And so the thing is that if we want to take basically a database, but which gives an incomplete description of the world. Okay, so I have a bunch of facts, but maybe it's really big, so it's kind of like a database nowadays. And then I want to add on top of it an ontology, because I want to be able to infer additional information using some background knowledge. Okay? Then people are going to be pretty unsatisfied if they can only ask these simple queries, because maybe before they were querying their data with database engines, using database languages, and they could make very complex queries. They didn't have any sort of reasoning or knowledge, but they could have complex queries. And so these people are going to be very unhappy if we take away their query language. Okay? They want to be able to say the same types, express the same types of questions as before. And so that means that in description logics, we've now moved to considering more complex queries that we can pose over our knowledge bases. Okay? And what makes them difficult is that they're complex queries from databases, but now we have a more complex setting because we also have knowledge. We have models instead of a single interpretation. So a very simple example here is, suppose that I have in a very really simple ontology here, just inclusions, okay? So mountain gorillas are primates, and mountain gorillas are critically endangered. And then I have some facts, probably have a lot more, but here are 3. So I know that Molly is a mountain gorilla who is kept at the Berlin Zoo, and the Berlin Zoo is a zoo, okay? Then a conjunctive query I might ask is something like this. So they consist of a bunch of atoms with variables and conjunctions between them, okay? So I might want to find all those pairs X and Y, such that X is a primate, and X is critically endangered, part of a critically endangered species, and X is kept at Y, and Y is a zoo, for instance, okay? And using the information here together, so this is just the facts, together with the information in our T-box, we would be able to get back Molly Berlin Zoo, okay? But if you just had the bare facts, you wouldn't be able to do this, okay? You need to have, admittedly, some very simple knowledge. Here is really nothing more than just a hierarchy of classes, but in many realistic cases, already adding this allows you to do a lot more when you're doing queries. Okay. So those are the main reasoning tasks. So now that we've defined our reasoning tasks, we can talk a little bit about how hard it is to perform them. So if I want to make an algorithm and get a computer to do one of these tasks for me, how hard is it going to be? So there have been really very extensive investigations into the computational complexity of reasoning. People have considered a huge variety of different description logics, ranging from very, very simple things that aren't much more than taxonomies, all the way up to incredibly expressive things. Still, of course, not all of first-order logic, because we want to remain decidable, but you can really say quite a lot of things. And they've considered various reasoning tasks. So for instance, if we look at things like satisfiability, subsumption, instance checking, these turn out to basically always have the same complexity. They're interreducible. But once we move to conjunctive queries, this actually requires completely new algorithms and often has like a different complexity, okay? And there's actually a variety, I will discuss on the last slide, that there are also a lot of newer reasoning tasks that are very relevant, and for those also people have studied the complexity of them. Okay? So nowadays we have quite a good understanding. So here what I pictured, and unfortunately it comes out a bit fuzzy, is there is a website with the description logic complexity navigator, and you can click some different boxes to say which things you want to put in your description logic. And once you do that, and you click go, then it's going to display the complexity for you and also the references to where this was proven. Okay? It only handles the so-called expressive description logics. There are some more restricted ones we consider nowadays that aren't there, but it's still a useful resource. And here's just a picture which has, among the expressive description logics, all the different relationships and so on. So you can see, and this is just some of the logics that people consider. There's really a whole slew of them. Okay? Now, what is the takeaway message from all this work on the complexity of reasoning? Well, the first thing is that it's pretty bad. Okay? If we look at the computational complexity, so I don't know how many of you have seen this before. So are people, for instance, have some of you seen like NP complete? Is this something you've seen? Okay, so NP complete is a class that we don't know for sure that it can't be done in polynomial time, but we strongly suspect that it can't be done in polynomial time. And so for a long time people said, oh, our problem's NP complete, ooh, we're not going to be able to handle it, okay? The case, what we know with description logics is that for most of the description logics that have been considered in the literature, reasoning, by which I mean satisfiability, subsumption, and so on, is X time hard or worse. So X time is the class of things basically that take exponential time. That's basically the definition of it, okay? And so for these, it's not just that we suspect that it's intractable, we know that it's intractable. Of course, the good news is that this is a worst case complexity result. It means that I can find some ontologies, and you have to craft really nasty things in them, okay? For which, and some data sets for which I can get this result. It doesn't mean that necessarily the things that we encounter in practice will necessarily be as bad as this. And this was why there's still hope even for the logics that have this bad complexity result. Nonetheless, it does mean that we have some challenges if we want to implement fast reasoners for these logics.
But
Yeah.
does it have to do with the fact that, say, classical logic, if I'm correct, perhaps, it doesn't have anything like computable model, right? So it's
Yeah, so the thing
that
is,
sort of logic somehow it's very different from what you have algorithmically, and that's why it just goes.
well, I guess what you can see it as is that, okay, for us, in some of our description logics, okay, I mean, first of all, a difference with first order logic is we are decidable for most of the ones we consider. The big difference is that in some cases, we do have finite models even. We can show that if it's satisfiable, it's always satisfiable in a finite model. However, the size of these models can be very large. And so basically, the size of the model that you need to look at could be exponential size. And that is what kind of gives you this here. Yeah? So there's a variety of things that come together to make it hard. Actually, different combinations of our constructors will move you to this X time. But a main idea is that even if we can either actually come up with a model, like because it's finite, or we can come up with a finite representation of a model, these typically are very large, and this is what causes problems. Yeah. Okay, so another thing that came out of all this work is that people identified useful tractable description logics, but by which I mean description logics for which we can do reasoning in polynomial time. And the thing is that in the very beginning, actually, of description logics, people, because they found out that some things were NP complete and they were very worried, so they tried to restrict things, but what they came up with were logics that were unusable. Nobody in their right mind would express knowledge using these logics. The interesting thing is that more recently, like starting from like the 2000s, people played with different ways of restricting it, and they came up with ones that are actually very relevant in practical applications and are possible, have a polynomial time reasoning, so that's a very nice development. And nowadays people work really on both, because the idea is that now that we have an idea of the complexity, when you need to do some modeling, you choose the weakest logic that will meet your modeling needs, okay? So you have these complexity results to guide you, and you can see, oh, well, maybe I should try to avoid adding this because it will take me from being polynomial to something much worse. Of course, in the end, if you really need very complex modeling, then maybe that is more important than being able to go fast. Okay, just to, and I'm fairly close to the end, so don't worry. Just to illustrate a little bit this complexity versus expressivity trade-off. So this is a very standard description logic. This is actually the one that is pictured here. It says base description logic ALC. So this is a really standard one. And it basically has the Boolean things and the existential universals. Okay, so it's really natural. And it's kind of naturally comes up if you take like the basic modal logics and you kind of try to find the corollary description logics. Okay, so it's very natural. And for this one, you can show is X time complete. Okay, I already told you this is often the case. And then you can add many things to it actually and stay X time complete, so not increase the worst case complexity. So for instance, if you add these inverses, which is a very natural construct to have, then you stay X time complete. Okay. Now let's consider what happens with EL. So EL is a very interesting description logic. It's very simple, as you can see here. Yeah, basically we have conjunction existential, and that's just about it. Okay. Why is it interesting? Well, earlier on I discussed these big medical and biology ontologies. that for most of them, this is what you need.
What about negation? It's not as...
No, they don't really use that so much. No,
Why biologists doesn't?
I'm just saying that this does most of what you need. There's actually some weak forms of negation you can add to this to do disjoint classes. That you can add without... So simple forms of negation in the form of disjointness, you can add it, it doesn't change the complexity, so this is okay. So you need to often go slightly beyond this logic to express those ontologies, but still we are polynomial time. So this is very good because those really huge ontologies, they're really big, right? So if we used a very complex logic, it would be very hard to do. Okay, so what happens now if I take, well, it was natural to add inverse roles here. What happens if I add inverse roles to this very weak thing? Boom, we're at x time complete. I mean, that's really surprising, right? It doesn't look particularly dangerous. I don't have negation. I don't have disjunction. I mean, and nonetheless I move up to x time complete, which shows you that, I mean, this work of mapping the landscape is actually, it's non-trivial. I mean, the results are not always obvious, and it's important for practitioners to know that when they move from this to that, they have this huge jump in complexity, and so what they can expect in terms of times for computing, for instance, the hierarchy of classes is completely different, and that's important to know. Okay, so this is my second to last slide. So just to give you a really high-level idea of what do these reasoning algorithms look like, okay? So, first up, if we look at these expressive DLs, so things like ALC or beyond, okay? Then the idea would be, say, if we want to determine whether this subsumption holds, we're going to try to build a counter model. By which I mean a model that satisfies everything in T, in the T box, and such that I have an individual which is C and it's not D. So what I'm going to do is I'm basically going to say, okay, suppose I have this guy here who's C and not D. And then I'm going to say, well, because the T-box says that, well, C implies blah, so I'm going to have to add that. And the T-box says that, well, I'm either an E or an F, so I'll add E or F, and I will try out. That's a bit of what makes it difficult. I will actually have to do case-based reasoning. I'll have to say, well, if I were an E, then blah, 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 blah. If I were an F, then blah, 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 blah. And I have to see whether, in the end, I'm able to build a counter model or a representation of a counter model.
Is it tableau method?
Yes, exactly, here. Yeah, yeah. So this is a very classical technique which is used for many logics, and this is the underpinnings of most of the reasoners for expressive DLs. Now, if you just take the standard tableau method and you implement it, it doesn't work. So people spend a lot of time working on very clever optimizations that allow them to actually make this work on reasonably sized ontologies, so hundreds or a couple thousand axioms. Okay? And this is kind of the state of the art, and it allows people already to do useful reasoning. Okay? Now, another method that's become very popular. This is kind of a very the basic idea is very similar to classical rule-based reasoning. So the idea is that if we're in a logic that doesn't have any disjunctions, then we're going to apply our axioms as rules, essentially, and just kind of see all the things that we can deduce, okay? We're just going to deduce more and more things, and then we're going to check whether the thing we were looking for, we derive it, okay? What makes this slightly more complicated is that we have this existential quantifier. So if I apply a rule, say, if I say that an animal has a parent who's an animal, and if I keep applying this, I could get kind of cycles. So you have to be a little bit careful to make sure that this forward chaining halts. But in the end, you are able, because there's no disjunction here, to kind of just build a larger and larger set of consequences, okay? And then to check whether the thing you want is there. And this is very helpful because we can take, for instance, that huge medical ontology SNOMED. So that had like 400,000 terms in it, and even more axioms. And you can classify it, so find all the relationships between the atomic concepts in a few seconds, okay? By using this type of idea, okay? So the idea is fairly simple, although you do have to do more than just what is done with traditional algorithms for rules to deal with this type of quantifications. There are still some things that have to be done to make it work. It's not completely trivial, but the underlying idea is fairly straightforward. Okay, and then a last one that is actually quite important, and unfortunately I didn't have a lot of time to cover it today, is that, okay, so I said that nowadays people are really interested in these more advanced forms of querying, like with these conjunctive queries, okay? And the problem is that they're actually quite difficult to answer. And so if we want to have, kind of database level performance, we need to work with simple, very simple ontologies. And we also, as much as possible, we like to exploit existing database tools, okay? And so people came up with this, another family of lightweight description logics called DL-Lite. And what was nice about this family of logics is that we can take our conjunctive query, and we can and then we look at our T-box, so the axioms, and we think about, well, what are all the ways that I could satisfy this query, given what I know about the axioms, okay? And then what I get in the end is a new query, which typically is actually much larger. That's a bit of an issue in practice. And this new query, it incorporates all of the relevant information from the ontology, but it's a database query. And now I can just give the database query to the database that executes it on my A box as if it were a database, and it gives me back my answers. So in a way, I managed to reduce the reasoning task of query answering, where I have to consider what happens in many different models, to the evaluation problem of checking whether something holds in the particular interpretation corresponding to my set of facts. And a very simple example, unfortunately I didn't have space to put something a little bit more interesting, is that if I have, for instance, I want to find all the primates, okay, all the primates. And in my ontology I'm going to have things like, well, a gorilla is a primate, and a chimpanzee is a primate, and so on. Then what I can do is I can kind of make a disjunction of all the ways of being a primate, and then I send that to the database. And it looks and sees, well, is this thing a gorilla? Is it a chimpanzee? And so on, and it checks. And the answers to this database query will be exactly the answers that I want with my semantics when I take the ontology and this query. Okay, so it's a way that we kind of can compile out the reasoning, okay? Okay, so I promised that I would conclude with some kind of current topics in description logic research. So where's the field going? And I think this will also answer some of your questions. The first thing, and here I'll be very quick because it's kind of obvious, we want things to go fast. We want this to be usable in practical applications. There's really no limits to how fast we would like this to go. And especially since now we want to deal with larger and larger T-boxes, so ontologies, larger and larger data sets, there's a real problem with scalability. So there's a lot of work to be done of building really efficient reasoners. Okay, so we've come a long way, but there's certainly a lot more to be done. Okay. The other thing is that, as I mentioned on more than one occasion during the talk, coming up with these ontologies is actually really difficult. And so we already saw that satisfiability testing or this classification, subsumption, these already give us some tools to help us figure out with what we're building is what we want. Okay? But that's not the only thing we would like. So there's actually a lot of new reasoning tasks people have come up with specifically for the purpose of helping people to construct and maintain ontologies. So the first thing is, okay, your ontology, it's unsatisfiable. It's got hundreds of thousands of axioms. What do? Right? You have no idea. You have no idea what to fix, right? So some people come up with services where they will find what are the axioms that are responsible for causing that contradiction, or which things are causing that unwanted inference. So if I find that in the class hierarchy things are not organized as I want, why? Okay? That's very important because otherwise it's practically impossible for someone to know what to fix. Modularity. So the idea is that people spend a lot of time, say, building snowbed. What happens if in my application I don't need snowbed, but I need a little piece of snowbed? Okay, so I want to reuse parts of existing ontologies. How do I do it? So how do I automatically pick out the relevant portion of an ontology for my application? So the idea is, say, I want to say, well, these are the terms in this ontology that are interesting to me. And then I want to press go, and it gives me the subset that I need. Okay? So there's a lot of work on this, and there are tools to do it. There are a variety of ways of expressing what is a module, what is a... Yeah?
No.
Oh, okay, I thought you had a question. Okay, so, there's of course a lot of issues in just defining what is a module, what makes a good module, why, and so on. And then afterwards, actually computing it is also very difficult. A third thing, I'm going along, I'm modifying, well, there's several of us maybe working on this big ontology. I'm making some changes, and now I want to see what are the differences between different versions of my ontology. Just as people who write code use versioning tools to check what changed, we would like to have that for ontologies. The difference is that saying just that we changed this is not necessarily very useful. What you'd like to understand is what are the differences in the semantics of the two. What are the differences in the inferences between the two? So you want to have a semantic difference between the two ontologies. What do they say about the world that is different? Okay? And that also requires some effort both to define what you mean by that and to compute it. Okay. And the last thing is that, as was realized during the talk, there are a lot of types of knowledge that don't so nicely fit into the framework that we've outlined here. And okay, I will mention a couple of them, but there's really many of them. And so, of course, people want to know, can we extend description logics, or can we come up with different types of description logics that will allow us to capture these other types of knowledge, which in some applications might be of crucial importance. So, for instance, people have introduced fuzzy description logics, just like fuzzy logic, to cope with vagueness, because sometimes people are not in a class or not in a class, they're in a class to a certain degree. Okay, you can be kind of tall, you can be very tall. Okay? Contextual information. Well, what does tall even mean? Even if we agree this to a degree, am I tall as an elephant or am I tall as a building? So some people try to come up with things where I can kind of reason about context within the description logic. Defeasible reasoning. So, I mean, obviously, both at some point in philosophy and also in computer science, knowledge representation, certain forms of non-monotonic reasoning have generated a huge amount of work because lots of common sense knowledge that we like to represent doesn't really obey the normal rules of logic. So, birds usually fly, but penguins don't. And so we'd like that if we have something that is a bird, we can conclude it flies. Now we learn it's a penguin, we don't want to conclude that anymore. Okay, so these require alternative semantics. They've been studied a lot for classical logic, but now how do we put these into description logics? And of course, since now we're really concerned about actually doing it. So a lot of work on non-monotonic reasoning. It was, yeah, what can we do with this one, what can we do with that one, but it was not so much concerned with computation. Here we actually want to have a system that does it, so this really gives us kind of new problems to deal with. And also inconsistency tolerance. Okay, so I've given you a lot of discussions about debugging ontologies and so on, but if nowadays we're going to have data, and data can be very big, data can be very dirty, we can't necessarily expect that at every time point the set of facts is coherent with the ontology. But does it mean that we have to just give up, throw up our hands and say I can't answer anything? No, because a lot of the information there is okay. And so you can adopt alternative semantics there to be able to get back meaningful answers despite the fact that you do have some contradictions. Okay? So that gives you just a little bit of an idea of where the field's going, and as you can see that it brings out a lot of classical issues in logics, in knowledge representation, and also in computation, because we really have a lot of problems to develop really good algorithms to do this. Okay, there you go.
Thank you.